Welcome to a new video in Core Systems Biology, Digital Twins and AI. We are approaching the end of block 4 and the end of the course. We basically learned all the methods that we need. So now it's about sort of zooming out and seeing what can we use this for, reminding ourselves of the importance of things. The sort of goal with the previous video of combining all of these different submodels into a bigger model, that we learned how to do that in this modular and hybrid and hierarchical way. Now we'll take this all the way to a digital twin. So here you see a copy of a person where you can look inside and see these different organs. So that's basically what we'll do now. We'll just learn some of the terminology of digital twins and then put this into sort of perspective of how this word is used and how now with the toolbox that you have from this course, how you can go beyond what most people are actually doing out in the world. So let's go to the definition of a digital twin. So a digital twin, quite generally, is a virtual copy, a computer copy that is representing an object. So you have some kind of physical object or physical process, and you have a computer copy of that allows you to study it in the computer. And some people here will add with a big emphasis that it's only a digital twin if you also have a real-time updating. So in our particular case, it would be that you have like a glucose sensor, or you have maybe a blood pressure sensor or something like this that allows you to continuously update your twin. Or whenever you have new data, you will update the twin. And some other people will say that, well, it's a digital twin anyway, but it's not an online digital twin because it's not connected to something that's online, or it's not an active digital twin. And they will say that if you don't have this sort of connection to data that is generated either continuously or at least frequently, then it's an offline or an inactive digital twin. And some other would maybe say that an active digital twin is what you have if you have one for a specific person. But if it's just for a patient in general, and it's not for a specific person, then it's an inactive twin. So if it's for an entire class of objects, then it's an inactive digital twin. And as you hear here, there is really no consensus on the definition of a digital twin, apart from this sort of very vague initial definition that it's a computer model, it's a computer copy of something, meaning that there is almost no difference between a mathematical model of something and a digital twin. And that's very often the case. It was the same thing with systems biology when it first came, and it still is to a large extent, that some people mean something and some other people mean another thing with the same word, all with the hope of sort of advancing their own interests. But it's good to know that there are these different additional terms that you sometimes hear, or additional requirements that you sometimes hear. And I also want to say that digital twins are used in industry since a long time. That's where it's been used the most, even though it's a sort of biological concept. The idea of a twin is of a sibling that you have that looks like you to a large extent, was born at the same time as you. And here we see a digital twin of some kind of engine or turbine or whatever that is. This is a Swedish news article from a network called Visual Sweden. They say now Norrköping, which is a city, should get a digital twin. And if you have a digital twin of a city, then you have all the houses and you have all of the landscape and even what happens below the surface with all of the different sort of electricity circuits and all of the other things that is sort of below the street level. all of that would be part of a digital twin of a city. So as you notice here, a digital twin can be of anything, can be of a space rocket. And of course, it can also be of a biological system. And two of the most common examples of how you use a digital twin in biology or biomedicine is that in one case here, you describe the biomechanics and the movements. So here you have the movements detected in real time and then projected via some virtual reality to a biomechanical digital twin that is moving like you are. So if you are moving here, this digital twin of you will also move, and you will see that in some virtual reality. So this is an example that is quite common of what is done. And the limitation here is that the digital twin that you consider is only considering the movement. It's not considering other things. And another very common thing is that you have a digital twin of the blood flow. That's maybe the most common thing. If you look out in a typical conference where you see how it's used. It's either biomechanics or blood flow. Those are the two most common things. And typically here, the anatomy is taken from an MRI or a CT scan of that person. So it's personalized in that way. And then you use some kind of simulation model to simulate the blood flow, either using partial differential equations or some lumped parameter model that we learned about in this course, and so on. And you can use this, for instance, to plan a stent operation. So if you need to surgically operate in a stent, you can do that in the computer first. And this is actually to some extent already used in the clinic. So that's pretty cool. But again, it's only used for the blood flow. And there is very, very few people, if any, that apart from us, that try to combine these things with each other, at least at the moment. But now you know that it's possible to combine models of different kinds. And this is exactly what we do. And this is exactly what you learn in this course. And in the previous video, we talked about how to do that. So let's just take a look at some of the different projects and submodels that we are integrating with each other in different projects. So here we have the Catalyst project, which is a New Zealand-based project, but we are a part of, and also Stratify, which also has to do with the brain. So this is the Soul Machines product, which has a very realistic face. And behind the face that you can interact with, you have the brain that has different areas here. And now you know that the different parts here that have an anatomically realistic placement, they are created by neural network, artificial neural networks. And some of the things that we try to do here is to sort of in our mechanistic models for the brain is to have neuronal networks that also have blood flow and also have the rest of the aspects of the brain to also get the connection to the physiology. In the same way, we have the blood flow type of simulations that I showed on the previous slide. And we had a whole video just dedicated to this type of blood flow simulations in block 1. And the biomechanical models, I will talk about them a little bit more in the last video of the block 4, so the final video. So here we have a biomechanics simulated in OpenSim, and this is an Unreal Engine type of simulation. And then we have this type of biomechanical metabolism type of simulations that we talked about in the previous video, where we have the metabolism. That means that the fat droplet disappears here because you change your diet. So this is a fast forward of a 2-week process where we have a fat droplet that disappears here. And the inflammation-based things in the Excite consortium centered around Örebro, and so on. So here we have M4 models, mechanistic models, multi-level from the whole body level down to the intracellular level, multi-time scale from, in the previous video, I showed you 40-year simulation down to sort of milliseconds, which is what happens inside the brain here, and multi-organ models. So that's M4 models. And And now you know, basically, at least in principle, how to combine these with each other. That these two you can simulate as parallel models. The metabolic models you simulate in this hierarchical way, where each organ is contribute with some part of the metabolism, glucose uptake, and fat consumption, and fat secretion, and so on. And these brain models in themselves here are also hybrid models that combine different types of formalism. The neuron and which has the neuronal networks with the neural networks with the blood flow models, and so on. So to sort of sum up a digital twin here, we have this hybrid combination, which has a mechanistic part that keep tracks of what happens inside the different organs. And this allows us to incorporate knowledge from ordinary biological and biomedical papers about what happens physiologically and biochemically inside of these organs. Here you can take personal data like sensor data, real-time time series, activity clocks, and so on. And you can also do images if you quantify them in such a way that they can go into a mechanistic model. And multi-omics you can also, to some extent, scale so that you can also use this in the mechanistic side of things. But these can also be used here in the black box machine learning type of models. So images are often used to quantify what happens in an individual. Multi-omics are often used in a black box type of way. And here you also have this big training data like UK Biobank, 500,000 patients that have been characterized so that we can calculate risk of a stroke. SCAPIS is a Swedish study with 30,000 patients. And so here you can take in the socio-demographics and other risk factors and hospital databases and so on. And they are typically not ideal for the mechanistic side because it's only one time point for each individual. But they are really good at for risk models. So here, because we have this ability to combine models in a hybrid way that we learned in the previous video, now we know how to make use of each of these data here in an optimal way and to combine the results in the end. So that from a point of view of a doctor, we can get a quick overview of the status of the patient. Doctor doesn't typically have much time, so he needs to get a quick overview, but then dig deeper, drill down as it's called. And then you can simulate scenarios. I showed you in the previous video simulation of 2 scenarios, one with eating a little bit more, one with eating a little bit less, and also exercising. You can simulate that treatment, but also medications. You can use this to communicate in a better way with your patient, and you can have this digital twin follow the patient after you talk to them, to the next doctor, or to the gym, or to the home, or whatever it is. And from a patient perspective, you can get a better understanding of your own health and why a specific diet is suggested, or a specific treatment. It doesn't have to be a diet. You can integrate all of your own data, and you're in charge of all of your own data. And you can get a personalized advice from an e-health coach that follows you throughout life. So all of this is sort of a basis for e-health. So to sort of sum up and see a long-term vision here for how you can use a digital twin. Basically at birth, you can collect some data, possibly donate some cells to a physical copy of yourself. I haven't really talked about this in this course because it's not really a part of the course, but there is something called organs on a chip that allows you to do a physical copy of you, where you have a little mini organs of you on a chip like this, and some first data that goes into the digital twin. And then whenever needed, you can donate new cells, stem cells, for instance, that you can differentiate over to these specific organs. And then you can do, whenever you want, physical experiments on a little mini you that you translate to your digital twin. And you can also get this from all of these wearable sensors like glucose and activity clocks and all sorts of other data that's generated about you all the time, to sort of have a continuously updated digital twin. that you can use throughout your patient journey, no matter what you do. You go to the doctor, when you design drugs, either individually for you or in general, because you have donated your digital twin or aspects of your digital twin, so it can be used for drug development, which is what we talked about in block 3. But also when you go to a concert, or you listen to music, or you go to an art exhibit, or you do some gaming online and so on, you can use your digital twin in all of these different aspects. And that's basically it for the sort of final vision here of how a digital twin can really transform healthcare to something that follows you throughout your health journey or your patient journey. And in the final video, we will talk about how to use all of this in a sound way.